So for conservative vector fields, we first have to make a few definitions for lines and regions in space so that we can understand the definitions and theorems later. Just kick him out of his spot and you can sit and write. So I'm going to draw the shapes and categorize them. So both of these are simple and both of these are not simple. And obviously both of these are closed and the other ones are not closed, also known as open. So this is a table, a chart. So if you have a closed non-simple, that's going to be the infinity symbol, or number 8. Closed and non-simple. So it's simple if it doesn't cross itself, then it's simple, and it's closed if it's closed, it's open if it's open. That should be clear. Now we have another set of these for regions. All right, so these are regions. Yes, but real quick. So these are connected? Not connected? And we have simply connected and not simply connected. So what does it mean to have a connected region? Connected region means one piece. So as you can see, both on the second row have 2 pieces each, so those 2 pieces are not connected. Now what it means simply connected? Simply connected means that within, no matter how many pieces you have, they're connected, you are able to put in a line that remains in that shape. So visually you should be able to categorize this very quickly, and we are going to use them in definitions coming up. And now big definition. I already mentioned this yesterday for conservative vector fields. Again, VF vector fields. So a vector field F is conservative if there exists a scalar function phi such that F is equal to del phi on that region. I'll put R2 or R3, so it can be in either one of them. Now vector field and del are both vectors, so I'm going to put vectors above them. Now yesterday we had an example of creating a gradient vector field by finding the gradient of a function. Now what we can do there is we can find the given any function, if you find a field from there, it's guaranteed to be conservative. Now in the praxis, you don't have this function phi, the potential function that creates the field. You have the field. You measure the field. You measure the electric field, gravitational field, magnetic field. You measure the wind. You go, you put those little sensors into the tornado, and they tell you the speeds and direction and everything. So you get to measure the field, and you have the field, and then you perform the procedure that we're going to learn now to find the potential function that generates that field. Because once you have the function, you understand the concept. So that is what we are after here. So let's take a look first at the test for conservative fields. Because if the field is not conservative, there might not be a function to generate it. So test for conservative field. Test for conservative vector field. So vector field F is going to be given to us as FGH as usual. So those are the functions in terms of x, y, and so on. Is a vector field on a connected and simply connected region D in R3, where F, G, and H have continuous first partial derivatives F is conservative vector field on the if following conditions hold. And now these are the ones that you need to know. Partial F, partial Y needs to be the same as partial G, partial X. Partial F, partial Z needs to be the same as partial H, partial X. And the only combination that is left, partial G, partial Z, partial H, partial Y. I will point out that in case of R2, this is the only test. So this is the only one tested. In order for a vector field in the 3D space to be conservative, all three conditions have to hold. As I said, you are going to find the vector field from measurements, experiments. And then you figure out if it's conservative, find the potential function. So let's immediately do the example of this because we need to have enough time to find one or two potential functions. And then we're done. So let's check testing for conservative vector fields. Any problem is fine. Let's do 12 because we can. Oh, it only has 2. What the hell. So f is equal to minus y, x plus y. So guys, this is your f, this is your g. So you simply run the condition. You are asking yourself if partial f partial y is the same as partial g partial x. If they are the same, it's a conservative vector field. If it's not the same, it's not. Very simple. So let's compute. Partial f in terms of y is -1 equals 2. Partial g in respect to 1 is 1. Not conservative. Very simple. I was trying to find something I can't. There's one. All right. Finding potential function. All right, focus. That's going to be interesting. So let's start simple and then upgrade. So in order for us to find the potential function, we would actually have to solve some of the partial differential equations. But since this is a separation of variables here, it's going to be fairly easy for us to do that. We're going to start with the simplest possible example, I guess. Minus y minus x. So let's go with that. So vector field f is given as minus y minus x. Now again, if the vector field is not conservative, you don't get to find the potential function in some cases. So you check first for conservative vector fields. And we know that this is going to work out because -1 equals -1, so we're good there. Just keep moving. And now we actually try and see what's happening here. So first, how do we do this? Well, we have the field. We know that field is equal to partial phi, which is actually, that's a vector, which is actually equal to phi x, comma, phi y. So guys, this is what we have in terms of phi x and phi y. This is what we have in terms of calculation for vector fields. Now, we start by claiming that the partial x is equal to negative y. We can start there. Partial x is equal to this. Now, what can I do? Well, I can integrate in respect to x to get rid of the partial derivative, right? Because partial derivative, this one over here, is partial derivative of phi in respect to x is equal to negative y. So how do this is a partial differential equation where I can do separation of variables by moving partial x to the other side and integrate in terms of x to get rid of it, right? So I integrate both sides, dx, and what happens is I get phi of xy is equal to minus yx plus some constant function in terms of y. So this is the key to understand y is the plus c, which is a function now. When you are taking a partial derivative back from negative yx in respect to x to get back to phi x, if you take a partial derivative here in respect to x, you get the negative y, and if this is over here either a constant or 0, or it's function in terms of y, when you take the partial derivative with respect to x, it's going to disappear. So you have to leave the possibility of this to be as much as you can, and that is actually a function of y. So now, when you are dealing with these kind of integrals, right, it's not just plus c, it's actually plus c, which is a function of, which could be a function of y. It could be 7, a number, it could be 0, but it could be also y cubed. So you have to leave it in there. Now, this is already your answer, but you can do better. This is already, see, it's already a potential function. Potential function is minus xy. But you can do better. You can actually figure out this. The trick is to now take the partial derivative in respect to y and set it to this one. This is your phi partial derivative y, this guy. So now you take the partial derivative of this, set it equal to the second one, and see what you get from that calculation. Let's figure it out. So I'm going to say over here, almost an answer. We can do better. So how do we do better? We find the partial derivative in respect to y of this, which is, in our case, negative x plus a derivative of this function, because now it's in terms of y. And we realize, maybe I should write, let me write it in pink. This is phi x partial, and this is phi partial y. And we set it equal to negative x. So we have the potential function answer. It's not full, but it's some shape of it. We take the partial derivative in respect to y here, and then we set it equal to the partial derivative in terms of y, which we had given in a field. And now from here, you quickly see, from this equality, you quickly see that c prime of y is equal to 0. If you are to integrate this, right, integrate both sides, you still get c of y is 0. Plus constant k, whatever. So that's the answer. Let's do another example. Let's go with problem 20. Vector field is now 3D, y, x1. Obviously on R3. So now I'm going to say this is your phi x, this is your phi y, this is your phi z. Now we compute this. We start by claiming the first partial derivative of phi in x is equal to y. That is partial phi partial x is equal to y. Separation of variables there gives us that the partial derivative of phi is equal to y partial x, and we integrate both sides. The left-hand side is going to give us phi in terms of x, y, z, because the derivative of d phi is just phi. And on the right-hand side, you are going to get yx, or xy, you can call it xy, there you go, xy, plus some function, which is a function of yz. Because this unknown function c in terms of yz could be anything. Could be sine yz, let's say. When you take a partial derivative with respect to x, it's just going to be 0. So you have to leave a possibility for that to be anything under the sun. Now this is already our partial answer. We can do better because we know that we can now find the partial derivative of this in respect to y and set it to the next. So partial derivative of y is just going to be x plus partial c over partial y, and that needs to be equal to x. From there, we see that our partial c partial y is 0, from where c is equal to 0. So we got 0 there. So now our, you can put some plus some constant k. We'll need that for the last. So now how does this look like? Yes, k of y. So it's equal to xy plus some constant in terms of z, right? And again, this is a partial answer. We can do better. So find the partial derivative here. It's going to be phi of z, and it's going to be 0 plus c prime of z, and that's going to be equal to 1. Aha! We just got that dc over dz is equal to 1. dc is equal to dz when you integrate both sides. Put this red because that's the next step. You get that your function c is equal to z plus whatever constant k, doesn't matter. So now we have our potential function. It's going to be xy plus z plus some constant k. Now this constant k is not that important because when you start taking the partial derivatives, it's going to die every time. What's important is the rest of the equation. That's the answer. It's a pattern that you keep doing and repeating. Let's go from scratch. The potential, the vector field is given, and since the vector field can be generated by the del of phi, that means that you have phi x, phi y, and phi z that you obtained by figuring out the del of phi. So now you start by realizing that each one of the vector field members are partial derivatives that came from the potential function. So we start with the first equivalence here, which is that. Separate the variables, integrate both sides. This is all stuff from differential equations that you learned in a separation of variables section in Calc 2. Separate the variables, and we get almost an answer, right? So plus c now is actually a function, not a number. So now what we have is we differentiate in terms of the next one from the list. So we did this one. This is up next. So we need to find phi y. We find the phi y by differentiating our best answer so far, and then we equal it to the phi y from the vector field. That equality tells us that partial c over partial y is 0, c is equal to 0, plus some constant c of z, because again the partial derivative of y of a function that is in terms of z is still 0. It's good. So this is our new best answer, and then we're going to do a little bit better because now we can find the partial derivative of z and set that equal to the third component from our vector, which is phi z, which gives us that 0 plus c prime of z is equal to 1, from where c prime of z is equal to 1, which is dc over dz. Integrate both sides, again, separate variables to integrate both sides, and you get integral of dz is z, and then plus some constant k. Add that back into the equation, and you have the answer. Now, let's say you are on the exam in 2 days, and you want to make sure that this is actually correct answer. It's very simple to check. You know that all you need to do is to find del phi. What's del phi? Partial derivative in respect to x for this one is y. Partial derivative in respect, and then 0 for z and 0 for k. Partial derivative in respect to y is x. Partial derivative in respect to z is 1. Is that where we started from? Yep. yx1. So when you find the potential function. Now, I don't know, as a student, this procedure to me was really cool because it was very structured. It was a lot of kind of messy things happening, but once you get it, it's really satisfying to do it, especially because it's so long, and then at the end, you have a very simple way of knowing that you did it correctly. Because all you need to do, it's like any integral in Calc 1 or Calc 2, if you were sufficiently interested in it, you integrate, and then when you're done with that, you take the derivative, and you can check. For me, that was great because I don't have to worry about whether the grade was good or not. I know it was good because I take the derivative, I check all the work that way. So you can find the potential function and then quickly take the partial derivatives and so on. So let's let's have you practice one of these. Here's the vector field. So try this. It says problem 22, yz, xz, xy. Yz, xz, xy. On R3, obviously. All right. I'll still write this. So you start with this one, and then you keep equaling to the other ones. It's a fun procedure. What happened? Yeah. How far? Hmm? I just found we can do in the final for 2 hours. Yeah, I'm gonna put the ocean waves high up. White noise? I don't know. We'll figure it out tomorrow. It could be beneficial. No. Oh, I need to switch. It is like a white noise.
You need a populated beach sound. People yelling.
Can we find 10 hours of screaming in agony? 10 hours of people screaming in agony. That's the final exam.
Epic sax guy, 10 hours.
Uh,
What if someone actually recorded rain?
Yep.
Epic sax guy. Fun.
11 hours.
Yeah, every 10 hours.
And 3 million have been spent 11 hours.
No, people actually play this all night. They put in the background to fall asleep, and I know a lot of people that actually play these sounds in the evening. I don't. I just pass out. See the bed, you go there, you pass out, you be unconscious for some hours, and then you.
I put on Yelping Dog after 10 hours. Let's figure it out. Just don't.
Put Mario.
In the morning,
The sound of
Don't worry about it.
The sound of sweaty legs on. The sound of sweaty legs on hardwood floor. 10 hours.
Can I call guy to bring Rosie in?
Oh, the transcript.
Yeah. Guess who's getting 0 on the test because he's not gonna be
You're not
here.
gonna be. Just put it right here. The whole cage.
So we're gonna do the tropical thing for the
Just want epic sax
rain.
guy. Epic sax guy. And you're.
Oh, you don't like the rainforest? He doesn't like rainforest, I guess. So we'll have to switch to rain. All right, let's solve this problem. And tomorrow we'll do the Green's theorem and the review, and that ends the course. Yay. So we start standard. Phi x is equal to yz. That means that partial derivative of phi, partial derivative of x is equal to yz, which is partial y is yz partial x, and then we integrate both sides. So we get phi of xyz is equal to xyz plus a constant function of yz. You forgot plus c? Oh, you got it. Okay, cool. All right, so now the step. Take the partial in respect to y, which is just going to be xz, plus the partial derivative over here in respect to z is going to be partial c over partial y. So now what we do? We set that equal to the second creature in our, which is xz. And from there, we conclude that partial c over partial y is equal to 0. You see that xz is equal to xz. So xz is equal to xz, and then there is nothing on this side, and you have still this. Just by simple comparison. Left and right sides. Which one? This one? Yeah, that's from the original vector field. And the other one is the partial derivative of the, that's why there's arrow there. So once we have this,
How come it wouldn't be like the first one within partial x? This would be xz partial y. Doing phi of y. Why? I'm not.
but when you take the derivative of x, y, z, xz is a constant.
Y?
Yeah.
So would it be xz respect to y would be
It is xz.
Yeah.
It says xz.
But where we get the what if we have to put y there? Xz y with respect to y. Take the
No, derivative of y is 1. We have a single y there. Derivative of y is 1. So now, phi of xyz is equal to xyz plus a constant in respect to z only, because we eliminated the one for y. Again, this is a partial solution, intermediate solution. We can take a partial derivative in respect to z, and we are going to get xy plus, we can just call this now dz, dc, dz. And we set this equal to whatever the third one is, xy. Wow. From where we conclude that dc, dz is equal to 0. So we just get the constant. So phi of xyz is equal to xyz plus some constant k, which is just a number. Again, that constant k is not important because as soon as we start taking derivatives to find the gradient which will generate the field, it's going to become 0 every time. So now, let's say you want to check this. We say del phi is equal to partial with respect to x is yz, partial derivative in respect to y is xz, partial with respect to z is xy. Every time k, which is a number, goes to 0. Is that the problem? Yep, that's it. All right, good. Nice. So tomorrow we'll take care of the Green's theorem, and we're done.